We have been talking about the complex numbers, and we have talked about all the basic rules, modulus, conjugate, and argument, and then geometrical representation, and then the multiplication, addition, and subtraction and division of complex numbers. Now we will talk about something more advanced, and that we call it okay, I need to off this. D. Moiver's theorem. Okay. Now the xy plane representing the state of complex numbers as just described before is known as Argand diagram. So we're talking about this. Here we count. So if we have a complex number z is a plus b iota, then we have a point a minus b, and then we count iota in this, and then we count a in this. So this is the Argand diagram. Okay. And it is also sometimes called the simply complex plane, or you can say complex plane. So this is known as Argand diagram, complex plane, or complex plane. Okay. The significance of geometrical representation of complex numbers begin to become apparent in the next result, which shows that we are talking about this result, which shows that complex multiplication has a simple and natural geometric interpretation. How? Okay, so let's give a theorem. To answer this how, let's give this theorem. 6.1, same name, Moiver's. Okay. Statement is, we have two complex numbers with the polar form is z1 is r1 cos theta 1 plus iota sine theta 1 theta 1. Z2 is R2 cos theta 2 plus iota sine theta 2. Then the product Z1 into Z2 is nothing but R1 R2 cos theta 1 plus theta 2 plus iota sine theta 1 plus theta 2. Okay. In other words, the product Z1 into Z2 has modulus R1 into R2 and argument theta 1 plus theta 2. You can prove this. we have this product. If we have this product, then we can write, because these numbers are just the constant numbers, so we can multiply them and write them in front. And then we have brackets cos theta 1 plus iota sine theta 1 and cos theta 2 plus iota sine theta 2 and r1 r2. So just see cos theta 1 cos theta 2 minus sine theta 1 sine theta 2 plus iota cos theta 1 cos theta 2, sorry, not sine, cos, but sine theta 2 plus sine theta 1 cos theta 2. And there we can end this multiplication. And now, if you compare these, you will get what? You will get R1, R2. Now, this is a formula which says that cos theta 1 plus theta 2. So this says cos theta 1 plus theta 2 plus iota. This says sine theta 1 plus theta 2. And so you have this theorem. Now, we have some more because of this theorem. The De Moivre's theorem says that multiplication of complex numbers A by cos theta plus iota sine theta rotates Z counterclockwise through the angle theta. For example, multiplication by iota rotates through pi by 2. So this says that we have a proposition which gives the consequence of De Moivre's theorem. The consequence is proposition 6.1. Let Z is a complex number let n be a positive integer, then if you multiply Z n times, you will get r power n cos n theta plus iota sine n theta. And if you take the minus n powers of Z, you will get r power minus n cos n theta minus iota sine n theta. That's how powerful the De Moivre's theorem is. And to show the proof of this proposition, we have number 1, apply theorem 6.1. Applying theorem 6.1, with Z1 is Z2 is Z gives Z square, which is Z into Z, which is R into R, which is cos theta plus iota sine theta plus theta, which is nothing but R square cos 2 theta plus iota sine 2 theta. Repeating n times, we get Z power n is R into R n times cos theta plus theta plus iota sine theta plus theta is nothing but R power n cos n theta plus iota sine n theta. This is part 1. Part 2 is, first we need to know how to observe minus Z power minus 1. So Z power minus 1 is 1 over Z, and that is 1 over R into cos theta plus iota sine theta. Okay? And this I can write further is 1 over R by the rationalization. We can write 1 over R cos theta minus iota sine theta divided by cos theta plus iota sine theta into cos theta minus sine theta. Okay? And if you solve this, you'll get what? 1 over R cos theta minus iota sine theta. Hence, Z inverse is R minus cos minus theta plus iota sine minus theta, which proves that for n is equals to 1, it is true. Which proves the result for n is 1. N, for general n, we have Z power minus n is nothing but Z power minus 1 power n. So Z power minus n is Z power minus 1 power n by part 1. We can write this as R power minus 1 power n cos minus n theta plus iota sine minus n theta. And if I write this, I will write it as R power minus n cos and theta minus iota sine and theta. This is the proof. Now we give some examples and then we can talk about more. Okay. We calculate example 6.2. We say calculate minus under root 3 plus iota power 7. We first find the polar form. So solution, we first find the polar form, and then that is so this is 1, this is under root 3, this is z, this is alpha. So in the diagram, sine alpha is 1/2. So alpha is pi by 6. And argument of z is 5 pi by 6. Also, mod of z is 2. So the polar form of z is 2 into cos plus the sine 5 pi by 6. Okay. By proposition 6.1, what we get? Z power 7 is minus under root 3 plus iota power 7. That is 2 power 7 cos 7 35 pi by 6 plus iota sine 35 pi by 6. And which you can still write it as we can also write it as cos minus pi by 6 plus iota sine minus pi by 6. Subtracting 6y from the argument 35 over 6 by subtracting 6 pi from 35 pi over 6. You can write this. Okay. Now we know cos minus pi by 6 is under 3 over 2, and sine minus pi by 6 is 1/2 minus 1/2. So minus under root 3 plus iota power 7 gives 2 power 6. Two power 6 root 3 minus iota. Gives 2 power 7 under 3 over 2 minus 1/2 is 2 power 6 under 3 minus iota. Okay. We can do another example, is 6.3, which says that find a complex number W. Find a complex number W inside C such that its square is minus 3 minus under root 3 plus iota. Okay. From previous solution, we know this. So if we define W, then W is going to be under root 2 cos 5 pi over 2 into 6 plus iota sine 5 pi 2 into 6. Okay. Yeah. Then by proposition 6.1, we know that W square is minus under root 3 plus iota. Note that under root 2 cos 5 pi over 12 plus pi plus iota sine 5 pi over 12 plus pi works equally well. By theorem 6.1, this is equal to W into cos pi plus iota sine pi is minus W. Now we talk about the notation. E power I theta. Okay. Now it is somewhat cumbersome to keep writing cos theta plus iota sine theta in our notation for complex numbers. It's very hard, like takes time. We therefore introduced a rather more compact notation by defining that e power I theta is actually equals to cos theta plus iota sine theta for any real number theta. This equation turns out to be very significant when e power I theta is recorded as an exponential function, but for now it is simply the definition of the symbol e power I theta. Now, for example, we can write e power 2 pi iota is 1, e power pi iota is -1, e power pi by 2 iota is iota, and e power pi by 4 iota is 1 over under root 2, 1 plus iota. Okay. Also, for any integer k, e power I theta can also be written as e power I theta plus 2k pi. Each of the complex number e power I theta has modulus 1. And the set consisting of all of them is the unit circle in the adjoint diagram. That is the circle of radius 1 centered at the origin. Let's write that. Each of the complex numbers e power I theta has modulus 1 and the set consisting of all of them is the unit circle in the adjoint diagram. That is the circle of radius 1 centered at the origin as follows. Okay. Now e power I theta. This is 1 point. This is theta. Okay. The polar form of the complex number z can also be written as z is r e power I theta z is I e power I theta, where mod of z is r, and then argument of z is theta. Now, for example, minus under root 3 plus iota in this notation is 2 into e power 5 pi iota over 6. De Moivre's theorem 6.1 implies that e power I theta into e power I theta is nothing but e power I theta plus theta, and proposition 6.1 says that for any integer n, e power I theta power n is nothing but e power I n into theta. For these facts, we begin to see some of the significance emerging behind the definition of this, and we give the proposition 6.2, which says that if z is r into iota theta, then z bar is r into e power minus iota theta. 2, let z is r into e power iota theta, w is s into e power iota theta in the polar form, then z is w if and only if r is s and theta minus phi is 2k pi, with k is an integer. We can prove this. 1, we have z is r into cos theta plus iota sine theta, and so z bar is r into cos theta minus iota sine theta, which is r into cos minus theta plus iota sine minus theta, and this is nothing but r into e power minus iota theta. Proved. 2, if r is s and theta minus phi is 2k pi with k in z, then z is r e power iota theta, which is s into e power iota phi plus 2k pi, which is s into e power iota phi, which is W. So it is true. This does the right implication, right to left implication. So this was to show what is the statement. Statement is if these two are equal, then these two are equal. So this is this part shows this. Now we will show this part, which says that suppose these two are equal, then mod of them is also equal. So R is S, and also e power I theta is e power I phi. Now e power I theta is e power I phi, then e power I theta, e power minus I phi is e power I phi into e power minus I phi, then e power I phi minus phi, which is 1. Then e power I theta is 1. Okay. Then cos theta minus phi is 1. Sine theta minus phi is 1. Sorry, is 0. Is 0. Then theta minus phi is 2k pi with k in z. Perfect. Here we will end this part of the chapter. In the next part, we will talk about the roots of unity.